Alright guys, so this is where we left off yesterday. Just to recap, the empirical rule said that 68% of our data falls within one standard deviation of the mean, 95% falls within two standard deviations, and 99.7% falls within three standard deviations. I'm having good luck with this today. Anyways, we're going to go to the empirical data example. There it is. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. was 64.2 inches. So there's your mean height, with a sample standard deviation of 2.9. Estimate the percentage of women whose heights are between 58.4 inches and 64.2. So if we go back and look at our chart, your mean is in the middle here, right? And since your mean is there, and then that was 64.2, and then the standard deviation is 2.9 inches. So this would be 64.2. Struggle is real today. Come on. So this is 64.2. Then this would be 64.2 minus 2.9. This would be whatever this is, minus, 64.2 minus 5.8, because that's two standard deviations, and so on and so forth. And so if we're looking for how much is within one standard deviation of the mean going down, we do 64.2 minus 2.9. It gives us 61.3 there. The next one would be 58.4. So what our question was asking was, what percent of women whose heights are between 58.4 and 64.2? Now, 68% falls within one standard deviation, but that's above and below, right? So here would be 34% between here and here. But it's actually looking for between two standard deviations out below and 64.2. So that's 95% for both distances. So we just cut that 95% in half. And that gives you 47.5%. So that's our answer to the question. We would estimate that 47.5% of women are between 58.4 inches and 64.2. All right. That takes us to our next one, which is Chebyshev's theorem. Ow. Chebyshev's theorem says the portion of any data set lying within k standard deviations of the mean is at least 1 minus 1 over k squared. So when k equals 2, in any data set, at least 1 minus 1 over 2 squared, or 75% of the data lies within two standard deviations of the mean. When k equals 3, in any data set, at least 1 minus 1 over 3 squared, or 88.9% of data, lie within three standard deviations of the mean. we continue this, we could go up to 1,000. So it would be 1 minus 1 over 1,000 squared. So that would be within 1,000 standard deviations. That would tell you how many or how much data would fall within 1,000 standard deviations for any data set. Okay. So here's an example of Chebyshev's theorem. Age distributions for New York is shown in the histogram. Applies Chebyshev's theorem to the data for New York using k equals 2. So if our mu is 38.8, right, then the standard deviation, this says that if we use this, would be 1 minus 1 over 2 squared, to give us 75% of the data falls within 2 standard deviations of the mean. So if mu is 38.8, then that would tell us 75% of the data falls between, well, 2 standard deviations would be even lower than, so it'd be negative years. Below and above would be 38.8 plus 45. So basically we know that 75% of the data is going to fall between, if we double this, that would be 2 standard deviations. So 2 standard deviations is 45. And then we subtract 45 from 38.8. That would give us negative 6 something. 38.8 minus 45. Yeah, negative 6.2. And then we have to go 2 standard deviations above the mean as well. So we would do 38.8 plus 45, which give us 83.8. So in the end, we would be able to say that 75% of the data falls between ages, then if our first age is negative 6.2, we can just start at 0 because you can't be negative 6.2 years old. 0 and 83.8. By the way, that is at least 75% of the data falls between those 2 ages. So it's actually really simple. Figure out what your percentage is using Chebyshev's theorem in this model. 1 minus 1 over whatever the k is to find your percentage. And then you go 2 standard deviations below the mean, 2 standard deviations above to find what the age range is. In section 2.1, we did frequency distributions. The formula for the sample standard deviations of a frequency distribution is sample standard deviation equals S, which equals the square root of the sum of x minus x squared times the frequency all over n minus 1. Okay? And in this case, our n, or the number of entries, is going to be the sum of the frequencies. Okay, so first we're going to find the standard deviation for the group data. So you collect a random sample of the number of children per household in a region. Results are shown in the table. Find the sample mean and sample standard deviation of the data set. So in our first chart, we're going to have our x's, and your x's are going to be 0, 1, 2, 3, 4, 5, ugly 5, and 6. Then we're going to have our frequencies. So how many times does 0 come up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many times does 1 come up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 2, 1, 2, 3, 4, 5, 6, 7. Threes. 1. That row is dead. 2, 3, 4, 5, 6, 7. Fours. Only 2 of those. Fives. It's only 1. And sixes. There's 4. Add these all up. 10 plus 19 is 29. Plus 7 is 36. Plus 7 more is 43. Plus 2 is 45. Plus 1 plus 4 is 50. So we have the right amount of frequencies. Now, we have to find x times f. And the reason we have to find x times f is we're going to have to find our x bar, or the mean of our frequency distribution. Okay, easy way to do this, just stat, edit, clear my list out, and just enter all my frequencies, or all my x's in. Go over to L2, enter all my frequencies in. Can't. Okay. Then I can go over to L3 and then do second L1 times second L2. That'll give me all my x times f's. It gives me 0, 19, 14, 21, 8, 5, and 24. That's not, some people might wonder whether that's worth pushing all the buttons to even get to this point. It's up to you. Now I can add all these up. So I'm going to go second, stat, over to math, sum, second L3. So that gives me the sum of xf equals 91. Then to find what our x bar is, it is the sum of xf over n. Whenever we do the sum of xf over n, it gives us x bar equals 91 over 50. You just solve that. Answer divided by 50 It gives you x bar equals 1.82. Now, if I'm thinking about this, I need x minus x bar I'm going to need x minus x bar squared, and I'm going to need x minus x bar squared times the frequency. So basically the only list that I can clear out here is list 3, because we're never going to need x times f again. I don't know why that moved. So I can clear that out, and now I need to find what my x minus x bar is. And so now I can do L1, so second, L1 minus what your x bar is, which is 1.82. So that gives me all my values for x minus x bar. I will tell you there's no secret to these ones to the end that's going to help you get anywhere that you need to be, that I know of anyways. So like yesterday we just pushed the one var stats button and it took us where we needed to be. But I don't think, to my knowledge anyways, that there's any button like that for the frequency distributions. Okay, we can move on to L4 now. Let's go up. Now, we're really taking what's in L3 and squaring it. So you just go second, L3 squared. That gives us L4, which is 3.312, 0.672, 0.032, 1.392, 4.752, 10.112, and 17.472. So that's our x minus x bar squared. Now we take that and multiply it by the frequency. And remember your frequency is in L2. So now this is going to be L4 times L2. So second, L4 times second, L2. And that gives us L5. So 33.124, 12.776, 0.227, 9.747, 9.505, 10.112, and 69.89. All right, now that we have all those, remember that our formula was the sum of all of those. So, for second quit, remember that's in the L5 category. Second list, there's math, go down to sum, that's number 5. And it's the sum of L5. That's going to give you the sum x minus x bar squared times f over n minus 1. And this equals 145.38 divided by 49. And so we get 2.966. We'll round that up to 2.967. And now we have to take the square root. And you get 1.72. So your sample standard deviation of this is 1.72. Now technically we could use Chebyshev's theorem to figure out exactly what percentage is between like the first standard deviation. We can figure that out using this chart. All right, to compare variation in different data sets, you can use standard deviation when the data sets use the same units of measure and have means that are about the same. For data sets with different units of measure or different means, you use what's called the coefficient of variation. Coefficient of variation of a data set describes the standard deviation as a percent of the mean. So you're going to find the standard deviation in the mean and then divide them and multiply by 100. For a population, it's sigma over mu times 100. For a sample, it's S over X bar times 100. Note that the coefficient of variation measures the variation of a data set relative to the mean of the data. So what this is measuring is how far or how spread out the data is in comparison to the mean. Comparing variation in different data sets, table at the left, it's actually underneath now, shows the population, heights in inches, and weights in pounds of the members of a basketball team. Find the coefficient of variation for the heights and the weights, then compare the results. So, easiest way to do this is to go in and go stat, edit, enter all your data in. I'm going to clear all these lists out. Alright. So I'm going to enter my heights in first. Then the weights. You do stat, calc, one var stats, and that's going to give you your X bar for the heights, yeah, this thing is really not working today. So it gives you your X bar for the heights, which would be 89.4. Wow. So X bar equals 89.4, and then your S equals 59 point, we'll say 59.8. Then we can do weights. So we go back into edit, enter the weights in. $181, $68, $25. Then stat calc one var stats again. Your X bar for the weights. It's going to be 187.8. Your standard deviation for the weights will be 18.5. So now we're just going to compare the results, which would be coefficient of variation equals, then it's your standard deviation. Was it really 59.8? I'm going to redo that. I don't believe that it was actually 59.8. Hold on. All right, I went back. I don't know what I did for that first one, but looking at the numbers, I should have known it didn't even make sense. Seeing as how our height, the average that I had, was higher than any of the numbers, then I should have known that that was an issue. So your height X bar is 72.75, and your S of X is 3.44. Okay, now to find the coefficient of variation, it's going to be 3.44 over 72.75 times 100%. It's 3.44 divided by 72.75 times 100 gives you 4.72. 73 actually. Now we can find our other coefficient of variation. CV equals 18.5 divided by 187.8 times 100. Like you would think I would learn. You get 9.9. So basically when we look at this, we're looking at how do the heights vary in comparison to the weights. Your weights are 9.9, the heights are 4.73, so the weights vary more than the heights. If the weights were lower or a lower number than the heights, then you would say the heights vary more than the weights. That's why the coefficient of variation is important. It allows you to compare how the data for the heights compares to the data for the weights. Then we can figure it out because it's based off of the same type of calculation. All right, you can go ahead and start the even problems. I'm going to give you the rest of the class today, which isn't that long, Thursday and Friday, or Friday and Monday on top of that. All right, guys.